I think, yeah.
You had a finance class in here once.
Finance.
Was it? You ever use this room again?
Okay, should we wait or start? I think Dr. Huang
Dr. Han, yeah.
is it's a hard time to find this one.
Mhm.
Okay, let me just introduce Jerry while we are waiting. So I have your old resume, probably quite outdated, but this can show the time you are living in. So the master student right now, but my relation with him started probably 3 years ago, in 2022, he started as an undergraduate research assistant in my lab, and he involved in various projects and thesis. And after that, he decided to pursue master. Uh, so the project he's working on is funded by the Army Research Laboratory. So they are developing a lot of technology, especially the airborne system. So this motor is like one of the key components using those airborne system, especially for electrical, those airborne systems. So they're doing this kind of research, like a thermal management or thermal analysis of motor is very crucial for those futuristic warfare in preparation for the United States. So with that, I will hand it to you, and then you have probably some 45 minutes to present, and then some question answer, and then after that, we will have a private meeting with you to discuss your, readiness to graduate, and then you join and then hear the final position. Okay.
On the slides.
Oh, thank you.
All right, so this thesis presentation is about thermal analysis and experimental investigations of both radial and axial flux permanent magnet motors. So just for a little bit of an introduction, as I'm sure you all know, electric vehicles are gaining a lot of popularity these days. And so naturally, electric motors are also gaining that same kind of popularity. And there's a lot of benefits to electric motors over internal combustion engines or ICEs. So the first of which is that they're a lot simpler to design because their design architecture is a lot less complex in nature. There's less moving parts than internal combustion engines, so thus there's less maintenance that's required. And even from a performance standpoint, there's a lot more attractive qualities of electric motors. So you can see this general torque speed curve, and you can see that right off the bat, electric motors start with a very high torque, where with ICEs, you have to build up that speed before you can really get a significant torque out of that. So in addition to these, there's also the environmental benefits. So there's no direct production of harmful emissions, and you can operate these motors on renewable energy sources. So on the other hand, electric motors are a lot more susceptible to overheating than ICEs. So you can run a combustion engine at several hundred degrees Celsius without a problem. But even before you get to 100 degrees on a motor, it becomes problematic, and then there's permanent degradation of the performance. So for example, the electric or the permanent magnets can begin to demagnetize around just 80 degrees Celsius. And complete motor failure occurs when the coating of insulation around the winding melts, which typically happens around 150 to 180 degrees. Now, the only real way to prevent these problems from happening is by ensuring that the motor operates at a condition that will keep it below that maximum temperature. Now, there's two ways you can determine what that temperature is. It's either by iterative and expensive prototyping and experimentation, or by developing accurate thermal models, which is obviously the more economic way to go about that. So here's two main modeling approaches to the thermal modeling of motors. Now, the finite volume method is very common and it's used a lot, and there's a lot of commercial codes out there that'll let you run it using this method. Now, these codes will tend to be computationally expensive, but highly accurate and showing the physics in great detail. However, just setting up these simulations can take a very long time, from importing geometry to running all those meshing algorithms. But the plus side of that is it can be created for just about any situation with the same algorithms and code. Now, on the other hand, with one parameter thermal networks, and I'm generalizing for our interest a little more on this one. Now, they tend to be more quick and efficient, but not quite as accurate as the finite volume. You typically only get the basic heat flow and temperature information. However, the simulation setup is quick and efficient. You can typically set that up and change meshing in just a couple of minutes. However, these simulations are typically developed for a single situation. So you can create a model for a motor or create a model for an internal combustion engine. And you can only vary that a little bit. So there's not a whole lot of versatility with this approach. So the research objective here is it's a rather simple one. We're looking to develop an LPTN model with a significantly lowered computational cost while preserving accuracy. And one of the methods that allows us to do this is, instead of solving fluid dynamics for the convective heat transfer, we're just using experimental correlations created by other authors to estimate these heat transfer coefficients to handle the convective heat transfer. And of course, we want to accurately predict the steady state temperature, not just in the winding, but also throughout the motor. So just a quick summary of the existing literature. So there's some authors with similar efforts. However, a lot of them are more higher order and a larger complexity that are similar to that of the finite volume method codes. And there's also the unjustified use of setting thermal contact resistance values to increase their model accuracy. So with no real logical justification in the values that they choose. So here's kind of our overall approach and framework. So you have two experimental sides, and then those kind of come together to create that thermal model. So the first experiment is just the motor experiment. Now, the approach for this is you need to create a system that can, one, support and have a supporting structure for the motor to allow it to operate safely and mitigate vibrations efficiently enough so that you're not risking the safety of the motor. But you also need a system that can independently vary the speed and the torque of the motor. Otherwise, all the data you're going to collect is just going to be a straight line. For example, if you load it with a propeller and then run it across its range of speeds, those torques are going to be completely dependent of the speed you're running it at. So you obviously need a few different measurements for this. So for the models, you need torque and speed measurements, as well as electric voltage and current measurements. And then obviously you also need those steady state temperatures at each operating condition. Now for the other experimental side, we have the thermal contact resistance measurement. Now in motors, there's several pairs of materials that are in contact. For example, copper is in contact with aluminum, aluminum's in contact with steel. And all those properties of those materials are going to behave differently. So when you measure these values, you need to characterize each pair of materials. And that requires running a lot of experiments, including to characterize the effect of the important parameters, which are going to be the contact pressure and the heat input or the heat flow through those materials. So once you have a thorough understanding of those, you can use that behavior and the known conditions of those materials in contact to choose an appropriate value. So you then plug that value into the model that you're using. You apply those heat transfer coefficients that you calculate under the appropriate conditions. And you need to have a geometry to go off of with accurate dimensions. And we'll kind of get more into this as we go on because there's a lot to unpack here. So this is just to expand on that experimental methodology, right? So you need 5 measurements total. You need to calculate the electrical power. So that's going to be the voltage times the current, and then the mechanical power, which is torque times rotational speed. And the difference of those two is going to give you the heat generation, which is the most important input to the model. So here's the experimental overview of our radial flux motor experiment. So this motor is a low torque, high speed motor. It's a brushless direct current motor. And it's of course radial flux. So we do have those measurements that I mentioned before, but we also have thrust being measured with our torque sensor. So right now we're not actually using thrust measurement for anything. However, in the future, we may end up using those measurements to somewhat compare the performance of different propellers or something to that extent. So you can see we got magnets of different sizes here, and that's because our eddy current braking system, which is our torque applying system, needed to be upgraded to reach higher torques that are generated by the kinds of propellers you would use on a motor like this. Because initially with these smaller magnets, you were getting very low torques that weren't sufficient to use for modeling. So here's this eddy current brake. Now, I won't get too much into detail in the physics, but I'll explain the working principle here. So you have a metal disc and you mount that on the motor. And as it spins, you take these magnets and you send current through them. So it creates this magnetic field. And when that magnetic field hits the surface of that disc, it ultimately creates a braking force that opposes the rotation. So just like I showed those larger magnets, we also ended up creating a larger disc to increase the torque of the eddy current brake. So here's on to our next effort. So this effort is currently in the modeling phase. So I'm going to start off with showing the experimental setup. Now, it does look a lot different, but ultimately the principle is the same, right? So you have a combining gearbox here that achieves the same thing as the eddy current brake. So you have 2 inputs and an output. And a dynamometer is on one of the inputs and the output, while the MRAX 28 motor is on the other input. And while these work together, there is a way of constraining them by effectively planetary gears or other sets of gears that allow you to separately control the speed and torque of the MRAX.
Jerry, sorry to interrupt, but can you give us some context of this experiment setup? Where this facility is located and how it operates?
So this facility is located at the Army Research Lab in Aberdeen, Maryland. And this is their Hive system, which is hybrid electric characterization of electrical powertrain. So the MRAX is an alternating current motor, and it's also a high torque, low speed motor. And it is also liquid cooled. So it is pretty much the exact opposite of the last motor experiment. It has a lot of different characteristics. So it's controlled using a variable frequency drive, and then using the motor controller, that direct current is inverted to create that alternating current waveform. So this is the thermal management system for the MRAX motor. So you can see we have a cooling loop here, and the heat that is extracted from the MRAX motor is eventually dumped into the building's chilling unit. using a train of heat exchangers. So we have a few pressure measurements and several temperature measurements in this loop to estimate the amount of heat that's extracted from the motor. And then over on the right figure, we also have several more measurements. We have one measurement internal to the motor that measures the winding temperature. You have some infrared cameras that measure the surface temperature of the motor housing. And then you have 4 temperature measurements by K-type thermocouples that measure the temperature of the surrounding air. And this is all put in a safety enclosure while the cases are being run. And the shaft is connected to the motor for the torque application, but it's completely disconnected for the unloaded cases. So when we run these experiments, it's being run at the minimal flow rate, which is about 4 liters per minute, and aiming for an inlet temperature of 10 degrees Celsius. This is the last experiment. This is the thermal contact resistance measurement. So similar to the MRAX motor, we're using a cooling loop and we're sending cold water through this cold plate. Now what that does is it sucks all the heat that's introduced in this heater block by the cartridge heaters down through the meter bars and the specimens and outside of the system. Now, the goal of this is to minimize the amount of heat that's lost to the ambient air so that you're minimizing the heat loss, because the heat loss is a direct input for the calculation of the contact resistance. So any heat loss is a bit of error to the measurements and the calculation of contact resistance. So this also utilizes a mechanical press. So the user turns this handle and that turns a lead screw and that pushes the upper portion of this assembly down and creates a contact force. Now the user can use that and the load cell readings to make sure that they are achieving their desired contact force. And then they can use the geometry of the meter bars to calculate that contact pressure.
So there's no motor in this, right? I mean,
Right, there's no motor.
What are we doing here exactly?
So this is just the measurement of contact resistance for pairs of materials.
Thermal contact resistance.
Right. So you have 2 material specimens and you just apply a contact pressure and send that heat through.
So these materials could conceivably be in a motor.
Oh yeah.
That's the idea. You're just doing a material study here.
Yeah.
But how this testing setup can be, I don't know, maybe how does this test setup be related to the testing of a real model with motor? Is there any,
Because in the real motor, when you have heat flowing through materials that are in contact, you have a temperature jump across those materials that you can't solve using theory.
okay, so you're just calculating the material.
And the methodology will be shown in a later slide. So I think that'll clear that up a little bit. So next I want to talk about the YASA motor concept. So the MRAX is what's called a YASA motor, and that stands for yokeless and segmented armature. So traditional motors have a yoke. I obviously can't show it here because it doesn't have one. But the armature is this iron core or electrical steel wrapped with that copper winding. And in traditional motors, this is all one part. This armature, that electrical steel, it is part of the entire mass, and it's not just segmented like it is here. And by removing that and removing the yoke, you decrease the weight by a lot. So that's really the huge improvement mechanically to this. Now there's also a magnetic improvement, and that goes hand in hand with the armature being segmented instead of one large mass. Because in traditional motors, the magnetic flux would have to travel through one core and then travel around to the next one to exit back and complete that loop. But here it's just traveling in and then out. So you're reducing the distance that it's having to travel by a significant amount. And by doing that, you are not weakening the field by making it travel a greater distance. So you have a stronger magnetic field here, and allowing that to happen is really increasing your torque by a lot as well. And so the big thermal innovation here is really just hand in hand with that concept, but also showing the liquid cooling jacket here. Now, traditionally, there's been a lot of thermal research into finding a way to run these liquid channels closer to the windings so that you can cool it better and run it at higher operating conditions without overheating it. But with traditional motors, you couldn't do that without interfering with the magnetic flux flow path. But since you just have this single armature that's segmented here, you can run those channels right next to it and cool a lot more efficiently. Probably could go on this or on about this forever, but I think that pretty much covers it. One last thing here. It's not super easy to see, but you can see one, there's kind of these little sections in the fluid domain, which is what it's showing. And there's also a separating section. So this is two different levels. So you have two segments here separating these fittings. And then, so you have the inlet here and you go about 120 degrees and you have another one of those segments at the bottom. And that forces the flow from the bottom to the top to go around. And then you have another one of these here, which it has to travel around again. And ultimately it creates this closed flow path for this fluid to go. So I just wanted to illustrate that.
So Brian, this is liquid cooled. The other one is air cooled.
Right, that smaller one was just air cooled.
And who developed this one?
It was a Oxford, I want to say.
Has it been around for a while? That motor? Never seen
Yeah,
that.
this looks very compact actually. So
I think people.
so this is so I don't know. Are you going to build some model based on this motor?
Yes.
Okay. And then can you explain a little bit when we talk about the traditional liquid cooling system will impact the magnetic flux? This part can expand a little bit.
Right, so
Why the
say
new things will have much less influence on the magnetic flux interference.
it again.
Why the new motor design will have much less magnetic interference? Yeah, we're going to talk about this one, right? Yeah, okay.
Right, because the iron core runs between the channels, so it's not interfering with it. Right, that iron core acts like a beacon for that magnetic flux. So it focuses it down and inside this winding. But since your channels are not interfering with that path, you don't have to, you're not sacrificing that efficiency.
You mean it's because the flux now is inside, but the cooling, I see this is cold plate, right? The cold plate is outside. Is this what we're talking about?
Right.
Yeah, something like that.
And right, so this allows for a direct bypass of the winding. So you're cooling it, I mean, not even an inch away, just millimeters maybe. And you epoxy all these armatures in. So this aluminum hub is also really the structural support holding everything together. Right, traditionally you use steel, so it's a lot heavier, but you don't need that because you have this design. So we did conduct a motor teardown to take all the dimensions of all the parts to ensure model accuracy. So this figure A is just showing with those housing, that sleeve and those rotors removed, just bare. And then here in B, we're showing this location of the temperature measurement somewhere underneath this orange paste. Now we don't know exactly where that sensor is sitting, but this definitely narrows down the location. And then down here, I'm showing all the parts that were removed from the center core of that aluminum hub. So there were two bearings removed, a rotor hub, which you can see right here. It's basically a shaft. What we were surprised to find was this fluid seal, because we obviously thought that this aluminum hub was just going to have a wall to cut off the fluid jacket, but certainly due to manufacturing challenges, they weren't able to do that. So that was a necessary part. And there was also this ring that sat rather loosely around the rotor, and we were not able to determine what its purpose was, and we decided not to investigate any further because that wasn't crucial for our application. So overall, we created two different geometry models. The first one we created before tearing down the motor off of inspection and online resources and educated guesses. Now, this obviously didn't work because we did not accurately capture the most important part, which was the cooling jacket. We inaccurately treated that in the geometry because we did not originally know that this was a Yasa motor. But having the corrected geometry, we can now ensure that geometry is not causing errors in our models. We were surprised to see that a lot of the components were accurate after all of it. So there were very few parts that needed to be completely changed. So I just want to do another piece on kind of that cooling jacket. So it shows the separators right here. So it's pretty much just a rectangular section connecting these two walls. And then you have these tiny circular channels on each level. Now, the old model, it didn't have these circular channels. It just had these kind of rings around the radius of this core. And it also assumed that was all one level. So that was the main discrepancy. So it didn't have that cooling right next to the windings. So now for our methodology here. So we're using the old geometry in these figures. So the way we reduce that computational cost is by taking a 10-degree axisymmetric section, axisymmetric about that center line of the shaft. And we create that LPTN diagram, and it's simplified from the actual model. But right, you create that from this geometry by observing all the convection surfaces and the cross-sectional areas that that heat is going to be traveling through. So this is the construction of our models. And here's our handling of the forced convection. So we have three different convective scenarios. The first one is the scenario that's treated with airflow and rotation over a motor. So if your motor's on, say, a plane and it's driving a propeller and it's flying forward, it's going to have that airflow going over it. And of course, the motor's going to be spinning as well. So that's going to be a combined convection effect. And then you have this outer tube that's rotating, and then the stationary cylinder inside that is feeling the effect of that rotating air, and its heat transfer is enhanced from that rotating air. And then similarly, you have just a rotating disc here that is losing heat. I want to kind of clarify what those are representing. So, right, that first one is just the heat loss from this cover and the front and back covers of it. And the configuration B is these circumferential faces of that winding being lost. And then the last one is the flat faces of the winding that's being lost. I just wanted to note that there is not an existing correlation that can account for this incoming air velocity. So we're only able to account for the rotation of the motor. So this is our thermal contact resistance methodology. So kind of just repeating from before, the important parameters are the heat flow and the contact pressure. So this requires significant experimentation for a range of these conditions and several different pairs of materials. Right, so you can see over here that the heat's generated up top here, and then the cold water is sucking that heat through this column, these meter bars, and these specimens. Now, right, so this contact resistance is defined by the average heat flow through those specimens divided by the temperature difference between the surfaces. So our temperature measurements are not taken on the surface, they're taken in the centers of those specimens. So after you calculate that average heat flow, you have to rearrange Fourier's law to interpolate that temperature to the surface. Now you can do that because heat flow is constant through those materials, even though that there is a temperature jump, but the heat flow is constant, which allows you to use that for interpolation.
Good. So we have two colors. Each color represents one material.
So you have 2 meter bars,
Okay.
one there, one there. So this is all one mass.
Okay. And the one in the
These
middle.
2 specimens materials.
I see.
So right, we have not made a ton of progress with the thermal contact resistance. So currently for the models, we're just using online references for thermal conductance, and we're taking average values for the appropriate material. And we're calculating it by dividing conductance times contact area by 1. So you're taking the reciprocal of it. And that's the values that we're using for the models. So kind of starting to move on to the results here. This is for the radial flux motor experiment. So since there's a lot of vibrations that can cause errors in these measurements, you have to find a way to filter out those errors and get a clean signal. So using an analog low pass filter, you can achieve that. And it's just a parallel resistor capacitor circuit. And you can use a value of resistance and capacitance to set a cutoff frequency. So for this case, we set 4 Hertz as the cutoff frequency. So signals with frequency above that are attenuated. So I'm showing the unfiltered signal in red and the filtered one in black. And you can see as the motor turns on, it reacts in phase. Obviously you have these fluctuations, so it's only really present for a second. But afterwards, it's just the motor on, so we're not applying a load yet. So it does come back to 0 Newton millimeters of torque. But then once the eddy current brake is turned on, then it does move to a non-zero value. It's negative because of the direction of rotation and applied load, but it's still a finite value. And then that stays until it's turned off. So that's the analog low pass filter in action. And that allows us to take accurate measurements using our sensors. So this is the initial results for the radial flux motor experiment. So the first table is just using a propeller as the load. And then the second one is using the eddy current brake. So you can see here, you apply a throttle percentage using the pulse width modulation. And you can see that a torque is going to correspond to a specific speed. And that is the case across the whole range of operation. However, over here, you set different magnet voltages, so you can get different torque for any speed. And so instead of just getting a line of data, you're getting like a 2D map of data. So looking at these trends, we're reading the voltage and current off of a DC power supply display. So we're not taking precise measurements of that. And I'm thinking that that's creating a little bit of inconsistency in these trends. So in the future, we're going to need to find a better way to calculate that electrical power. Because I'm not super confident about these. The trends are not what I would expect, although they're not terribly off from what I would expect. But I do think more time needs to be spent on improving that. Now, for the MRAX motor, we initially used the DC measurements for the electrical power. So we did overestimate these values for heat loss. So you can expect that there will be overshoot on the models, especially as you go up in the torque and speed. Right, so we have efficiency ranging from about 75 to 85% for these conditions. And so this is the results. We're comparing the LPTN and the FVM model with the measurements for the no torque conditions and the torque conditions at 2000 RPM. So these results do show kind of similar behavior. Obviously, the unloaded ones, they don't depart quite as much as the loaded conditions do. And you can notice that the models agree a lot more with each other than they do the measurements, especially as you increase the torque speed.
I'm not a motor expert, but when you talk about temperature, the motor is a very complex mechanical system. Now, is an electromotor is even more complex, maybe. When you talk about temperature, you are referring which point?
The winding temperature.
The winding temperature.
So the temperature measurement.
In the winding.
Mhm.
But the winding is also building around inside the motor. It's a spreading, right? Something because there's a turn by turn, a lot of turns, right? Maybe they have this is a 3D component, right? Have turn. When you talk about temperature, you're on the winding, you're talking about which point? You're talking about the winding averaging temperature or what is the hottest spot?
So this is where the temperature measurement is under this post.
So you're only talking about this point.
Right. That's the temperature we're reporting in graphs.
But the question is that that point can represent the worst scenario of the winding. I mean, from temperature point, right? I think
Say that again?
that point can represent the worst scenario. Is this the hottest point or not?
It should roughly be because the winding should be the hottest part.
I know, but you see, the winding, it has dimensions, right? It's this is a ferrite core. I don't know if it's a ferrite or not. I think it may be that this is a nanocrystal. I don't know. This is a core, right? The winding is winding around that one. It's a whole piece of winding. You're measuring that point, but the winding has like inner surface or outer surface. But I believe the inner surface is hotter, right? But even in the inner surface, it has a top point, the middle point, the bottom point. There's a whole surface. My question is, are the temperature really evenly distributed or there's some difference there? Is my question. Maybe this is not a valid question. I know. Yeah.
So from a physical standpoint, we're not sure. But from a modeling standpoint, you don't get a constant temperature on that surface.
Yeah. For example, because we also design all the magnetic components, when I design transformer inductor, so the winding is a lot of winding there. So not every spot is the same temperature.
So Jerry, from next slide, I will show better information about the location of temperature measurement, also the different structure. No, the next one.
Next one.
This one. More. Yeah.
Okay, here.
So you are solving a 3D problem, but you're only presenting comparing only one location based on measurement and then just one location. But the 3D result will show the kind of 3D profile with the winding area.
Okay, and now see this is a green.
So not necessarily the highest temperature, but happen to be the location for measurement. Then we try to match it, try to compare.
So basically, you use simulation to find the hottest spot, then you do temperature measurement to verify this is the process.
So more like the
Trying to match
only
them.
information we have is a measurement, just one data point.
Okay.
And then using
how do
that,
you decide this is the point you want to measure.
yeah, but this will give you like a kind of like initial validation,
Okay, I got it.
and then whatever the result will be still valid because you validate at least 1 point.
Because the motor already comes mounted with a temperature sensor. So we didn't place that ourselves.
10% is there already.
Yeah.
Maybe they know. Okay, yeah. Because this is a complex problem. Even there will be some difference. To be honest, I don't believe it's a tiny difference. Sometimes the difference will be a lot from point to point.
So, right after looking at those measurements compared to the model results, we'd like to look at kind of the temperature distribution through the motor. So we've plotted these two different paths. So there's an axial path and the radial path, and they intersect at that anticipated measurement location. But you can kind of look at these paths and kind of think, well, the axial path is only really going through that part of the stator and then the outer housing. So the radial path is probably going to contain a lot more interesting information in the axial one. And you kind of see over here that that holds true, right? So you have this roughly room temperature value here, and you have a jump in this kind of U shape, and then a small drop back down. So it doesn't really tell you a whole lot about the behavior of the motor. But if you look at the radial variation, you can see starting at the shaft, as you get closer to that cooling jacket, it starts to dip down. Then after you're passing that cooling jacket, you get huge jumps from contact resistance, but also because you're heading towards the windings. And then you drop back after down to that outer housing. So you can really see how that proximity has a large effect throughout that radial path of the temperature distribution. And you can see these measurement locations here. We're running the 2000 RPM unloaded condition. So that did still have pretty good agreement with the measurements because it was a lower operating condition. So you can see that these distributions actually do agree well with that stator temperature measurement and then also that surface measurement at the outer housing. So lastly, we'll look at a parametric study to kind of inspect the impact of variation of certain parameters with the temperature of the winding. So we want to vary the coolant temperature, the liquid heat transfer coefficient, and the ambient temperature. And we're going to use the same condition for 2000 RPM and no load. So before I show those, So I want to show you that this hole right here is where the liquid jacket is being represented. So you can see here, since it's the old model, it doesn't have those circular channels. So there's actually a really small amount of surface area that's actually being represented there. So here are the results, and you can see that the heat transfer coefficient actually doesn't create much of a change at all. However, if you change that liquid temperature, it does have a pretty significant effect because that's scaling with temperature. And then here you have the ambient temperature, which has a little bit of change, but again, it's not much because that heat transfer coefficient is so low. It's just air. So now I want to move on and talk about the thermal contact resistance a little bit. So here we have the geometry model for the entire mechanism and assembly. Now, we're just running the thermal simulation, so we can just take the thermally conductive part of it and place it in there. And we apply a 50-watt heat input to the heater block, and then we hold the cooling channels of the cold plate to 4 degrees Celsius. And you can see the contour variation as you get more to the meter bars. So here's our experimental results. So first we have the load cell measurements. So you can see that it changes quite a bit over time after applying it. Now, copper doesn't have bad creep properties, so you can't really attribute this to that. But what you can say is that, okay, copper is a pretty soft material and it has a significant value for thermal expansion coefficient. So if you look at how these increase over time, you're already applying a load on them. So they're already in contact with force already doing it, but you're telling it to expand. So that force is going to increase as you increase the temperature of those meter bars. And that really explains why you have this kind of behavior. Now, we're thinking that there might be some DAC issues later in the steady state experiments, because this is pretty typical of what we get. We get some nice waveforms, but then we get some jumping up and down. And so we haven't been able to troubleshoot that issue yet. But you can see over here, I've listed what the heat flow calculated through the meter bar is. And they should be 50, but they're both pretty far off from 50 watts. So these temperature differences should be the same. They're actually pretty different. So we do have to figure out what's causing that issue. So here I'm comparing those steady state results from simulation and experiment, right? So by definition, a simulation is going to follow conservation of energy. But the experimental approach can often be quite different, at least in appearance. So you can see that these do kind of have numbers, similar numbers. Now, in simulation, we're not really using contact resistance values for these cases. But of course, in the real world, you have contact resistance. So that is probably compensating a little bit for the discontinuities we're observing in our measurements. Now, here I'm showing some isotherm surfaces, right? So our methods assume one-dimensional conduction through these meter bars, and that's going to be shown by this plane surface. Now, these isotherms, they tell us where a temperature is. So they create a continuous surface that's at a particular temperature. So close to the heat sink or heat source, you're going to have more of this spherical type of isotherm. And it gets that shape as it travels away from the heat source. But as you travel farther and farther away, it eventually molds into this two-dimensional plane. And that's when we achieve 1D conduction. Now, it can speculate a little bit about why we're getting these bad measurements. Now, one possibility is that there's not enough material in between the source or sink and measurement. But if that were the case, then the simulation should still give us the same result. But since simulation isn't accounting for the actual contact resistance that's happening, it could very possibly be because of something like that. So I have some graphs drawn over here, right? So as you increase that contact pressure, the contact resistance decreases exponentially. Now, we did try pretty hard to create flat surfaces between the meter bars, but on the micro scale, it looks kind of like a mushroom top like this. So when you push those two together, you are going to get deformation because copper is soft, but there's still going to be a much lower contact resistance towards the center because that's where the most contact is happening and you're increasing the contact pressure. So the pressure, as you travel away from that center line, it's going to be less and less. So the resistance theoretically is going to be higher and higher. And when that happens, you're going to get a temperature distribution that kind of looks like this, right? So you're going to have a small temperature jump across that center, but with that higher contact resistance as you travel out from that center line, that temperature jump is going to get bigger. So your temperature across the interface out here, out away from that center line, that temperature is going to be smaller on this side of the meter bar. So that heat flow is perpendicular to those isotherm surfaces. So right for this plane case, it's going to be one-dimensional. It's going to be in a single direction. But since this is going to create a curve, kind of like a much less exaggerated version of these, you're going to have heat flow in a bunch of different directions. And that could be what's contributing to those inaccurate measurements, right? So we should be getting 50 watts. We're getting 65 and 17.5. Now 65 is still a lot closer to 50 than 17.5 is. That's like almost an extra 10 watts. So that is most likely what the problem is. We've done a lot of testing to try to rule out other possibilities, but looking at the contact resistance really hasn't been easy to do. So it's hard to rule that out with the lab materials that we have available to us. So I want to draw some conclusions here. So for the radial flux motor experiment, the eddy current brake design was actually really successful. We do experience a little bit of resonance, but it's nothing that's detrimental, and it's something you can quickly move past to avoid a bigger problem without really getting any damage to the motor while passing. So the power calculations are appearing a little bit inconsistent with conservation of energy, and it's likely a measurement issue because it's not the type of trends that you would expect. And ideally, the structure should be redesigned because there's a pretty long unsupported length. So that's only worsening the vibrations that do occur. And the large disc isn't any help either, although you can't do anything about that. So for the MRAX motor modeling, so far we have done calculations based on DC measurements, but that's ignoring inverter efficiency and it's also ignoring power factor. So we are definitely overestimating the heat generation in the motor. So we're also estimating values for contact resistance, which could be potentially significant, but we truly don't have any way of knowing how much air is being produced by that. So until values of power factor and contact resistance are determined, there's plenty of uncertainty in that model. So for the thermal contact resistance, until the source of the unexpected experimental behavior is determined and resolved, the data gathered is completely meaningless. But once we resolve these issues, we can carry out these experiments and determine appropriate thermal contact resistance values for the models. So although these projects still have a long way to go before really producing tangible and meaningful results and accomplishing these objectives, we have made a lot of great strides to put these efforts in the right direction. So what began as little knowledge of the related physics and model behavior grew into a better understanding and a better understanding of the challenges that we are facing and the challenges that lie ahead. Now, before I end it, I do want to present a couple of slides about some pretty significant ongoing work. So there was a second analysis carried out to not use the DC current calculations, but instead use the alternating current calculations, although we still can't account for power factor, but we can improve the values that we're using and expect to see better results. So I can kind of compare the value here. So for this scenario right here, earlier we had about 475 watts. So it's almost cut in half here, right? So only 280 there. So you are having a significant reduction just by using the alternating current measurements or calculations instead of the direct current. So this is the unloaded heat loss. So I'm comparing the MRAX motor data that they posted on their website to our calculations. Now this is for the unloaded, we're still using DC because the motor controller it uses switching, right, to create that AC waveform. So the measurements that we're getting at those unloaded speeds, they're not fully developed waveforms because that current is still so low. So you're not going to get realistic results from the calculations for those unloaded cases. Now, you do see some pretty good agreement for the first couple of cases, but for some reason, once you hit that 2,500 RPM motor speed, there's just a big jump in the calculations. Now, the slope is still pretty agreed with. There's just this random jump here. So that's something we'll need to look at. Maybe it was an error with measurements or something, but clearly something not right here. And so using those reanalyzed measurements, I tried to compare efficiency maps. So we're just operating this condition, maximum 100 Newton meters and maximum 2,500 RPMs. So you can see we didn't really have much for 90 or 95% efficiency. But as you kind of get more towards 80 to 85, you are starting to see some resemblance to this efficiency map. So there's, it's obviously not spot on, but there is some resemblance. So we can see a positive result from it. So now we can take that new geometry and we can take a section there too. Now I'm using a 20-degree section instead of 10 this time, just to make it easier to mesh and not have to deal with any problems with conformity for the bearings. But you can see this dark spot is where the cooling jacket is. They're kind of half channels because of the way that it's cut, but you have this area too. This is that inner ring, that reservoir in the cooling jacket, and these are the channels that bypass the winding.
You solve the fluid as well?
No fluid. So we're still using the heat transfer convection correlations. So this is for the 80 Newton meters, 2000 RPM case. So this is the highest heat condition that we ran for the previous model. So here we have 50.1 degrees C, and that's kind of an average location of the paste. So I tried to put it a little forward than the very back of it, but a little back from all the way up there. So this is kind of like, say, the centroid of the paste. And this reads off as 50.1 degrees Celsius, where the measurement is 46.6. So that's exactly 3.5 degree error, which is pretty good. Using this new geometry and that increased convection area for the liquid jacket, as well as those calculations from the alternating current. So, well, I did an intern actually at the Army Research Lab last summer, and one of the other interns showed me a really great company called Gleason, and they are really huge on electric vehicle engineering stuff, informative. They post all these ebooks that are really great for learning. And he also worked with them in research. And he told me that they were going to help bring a gear theory class to Penn State, which I thought was really cool. But there was also the table of thermal contact resistance from SolidWorks. And Gleason is also where I got that general torque speed curve for electric motors and combustion engines. And that's the end.
I kind of you like in one graph represented the results from finite volume method, lumped parameter thermal model, and also experimental data. Did you do all of them, or some is done by other people? You did the modeling using finite volume? Or...
I collaborated with other researchers,
okay,
but I did eventually take over those efforts.
Okay, so you did the modeling as well as the experiment.
Oh no, I did not myself. The Army Research Lab researchers did the experiment.
Okay, okay. And you are more on modeling.
Right.
So we have like Army project for many years.
Okay.
And we do a lot of the thermal modeling for not only motor, but other like the batteries and other things. And then we use a summer internship as like one of the vehicle to send our student and then learn from them and then participate and then, in some education purpose. And then using the summer internship, we basically make a collaboration project so that student can take the lead and then do some, something and then bring some result to the school. This project actually, we had a two summer internship project in Bali. My first PhD, and then Jerry's the second one. So it's day back to probably 5 years ago of this project, from the beginning of these ideas, and then formulating this project, and then getting money, and then kind of organizing different activity here and there. So you see some history here, like a measurement of the big motor, small motor in the lab, and the modeling of the big motor, small motor, and then some like the quantum resistance measurement.
Okay.
So those are like not happening at same time, happening at different time and different person and different places. So Jerry is like the one combining all those together and trying to make some good story out of it. So still there are many things to be done in terms of improving accuracy, in terms of putting all together makes sense. The ultimate goal for the Army project is developing tool for Army engineer
I see.
or soldiers who has a very little or minimum knowledge on the thermal problems. So using this tool, they like to rapidly develop any kind of the UAV platform from big to small, any sizes. So having a tool is very essential. We are the one of the team of a very mega team. We're only dealing thermal management of those particular components there. So this project basically helping the military, the activity and those enterprise, and trying to develop some tool for that. UAV becomes now major weapon arsenal for the U.S. Army now. So we are glad we are part of that effort. Jerry was a great force for that effort.
So, Jared, if I understood right, the objectives of your work were to develop this lump parameter model primarily for two different motors, one that's air cooled and one that's liquid cooled.
Right. But ultimately, the goal is to, in the long term, develop one that can be used for any motor. So like a general.
Okay. And just looking at that model, it looks like there are no transient terms in there. It's just
It's
resistors.
all steady state.
It's just resistors. Resistor model. Why no transient terms?
Because the steady state temperature is going to be maximum at steady state.
You're not worried about any overshoot or anything like that?
I mean, you could, but for an operating condition, the maximum temperature is going to be what you reach over an infinite period of time. So even with transients, if you're not going past a certain condition, you're not going to go above that steady state temperature.
Okay.
The UAV always fly transient, right? Not steady state, not constant speed, always up and down, different speed. So steady state is just one information of those entire this spectrum. And transient actually very valuable for designers and engineers. But there is some technical difficulty around that transient model.
Well, I can imagine. I was just,
Because
but I was,
if you look at the energy equation,
Yeah.
there are one term, is we call transient term, has the volume, mass, all the property. The other side, only conductions, heat generation. So without this transient term, the modeling is very simple. But if you include transient term now, suddenly it probably becomes, okay, no idea what you're going to do.
well, and I think this the steady model is very, very valuable and a good starting place. Just think maybe in time, the place this might go to think about transient aspects. But so what I really need to ask you though is if somebody was to ask you what the contribution of this thesis was, what would you say?
I would say to develop a model that has a low computational cost that can predict these temperatures.
And did you do that?
Yeah.
So I think you need to say that in your thesis. I don't think I saw that. And as I read the conclusions, I'm not trying to be critical. I'm trying to be helpful. As I read the conclusions, it sounded to me like there was a lot of apologizing that you were doing about not having gotten the results you were hoping to get. And I think you need to be a little more positive about it, because I do think you've contributed something. And the idea of actually getting a lump parameter model in place that matches your numerical or your finite volume model, pretty valuable. So it just didn't come out very strong that was what you did. And I think I would brag a little more than you have.
Okay. I think with this ongoing work, there's a lot more success too.
So actually, I think I have a very similar feeling that sorry. So I think this page is very typical what we're talking about. I think your thesis, your work so far, something good and something not be improved. Both of them are very obvious. So the work is doing very good actually. To be honest, I'm surprised to see so much work, because I can see there's so much detailed work, step by step, this hours and hours of hard working is impressive. This is the good one. But the other side is this page of reference, right? This is thesis. You print almost like a 40 or 50 minutes. You only have 2 references.
He's got about 20 in your.
Yeah, I only included references on.
I know. Even 20, to be honest, for your work, still not enough. I feel like you may include like the 50 or 70 or this kind of amount, because you see, in the printer, right, you have the different kinds of motor, but you don't have enough settings like this one, whereas sometimes we don't see which one is from you, which one from others. And I guess like Dr. Park talk about this project has some history, right? So that means some of your previous colleagues may have done some work, maybe already published in some formats. Then you can recite those kind of stuff, right? So this back to the very core comment from me is that this is a complex modeling work, and the title is very general. And it's very hard to find what is your specific part and contribution in this big project. So if you can make the story like for example, this picture, this sky is so big, right? You're describing this so big sky, the clouds, so many clouds, but there's a whole overall architecture of the whole work. But I'm doing this part as of this whole work. So have a very good, when you explain a story, have more focus on the overall structure and the modeling gaps, right? Then, but you are feeling this bit because you see their model, work may be doing later, right? So you can say this is the future work, but this is my work. Now you can see this is much more clear in as an overall structure. But again, this is a really a lot of work, I can say, yeah.
Okay. Yeah, so actually on this topic about references, I had a similar feeling that even 21 is not hot. However, I remember a few years ago when attending non-student defense, I raised a similar question. On one of the committee members says that, look at Einstein's 1905. So yeah, anyway, certainly you need to include what you need to include. So maybe you need to look at this again. So my question is really about your thermal contact resistance. That it is really complicated, even though it looks like simple, but really complicated issue. That effect by the surface finish and even the moisture, and of course the force applied. And you did a really nice experiment about this experiment, showed that how this force will affect your contact resistance. But the problem is that in your model, how do you know what is your force? Then you really don't know what exactly is your RC there, right? So how do you make the decision?
So right now we're just taking averages and we're not really justifying anything force related because we're not using force in our models. We're selecting the value of contact resistance and putting it in. So we would definitely need to learn more about the kind of contact pressures that are in those configurations of motors before really having a logical justification for selecting that specific value.
Okay.
Okay, do you have any further questions? We can dismiss you probably for 5 minutes.
Step out.
Yeah.
I'm gonna take this with me.
Oh, I've been recording the presentation. You want me to stop it for your?
Yes, it's about it.